Welcome to this web lecture on two echelon facility location problems. This is a continuation of a web lecture on facility location problems, which use the example of transportation of wood. And this is also where we're going to pick up now. So we have Woodworks BV, which operates several sawmills and transports the wooden planks to workshops throughout the Netherlands. They're currently moving to a new market in Belgium and they're planning their distribution network. And the one question that we're going to look in throughout this web lecture is, does it make sense to include the locations of the forests in the location decision? Let's first look into how we're formalizing this, how we're stating this problem. To expand their operations, Woodworks BV aims at operating one or more capacitated sawmills which connect their forests, which have a maximum amount of logging, with their customers, i.e. workshops, which have a certain demand. They aim at minimizing the total costs comprising of transport costs, operating costs for sawmills, and the handling costs at the sawmills. So if you look at this example down here, we have transportation costs both on the left and on the right, and in the middle we have both opening and handling costs. So the first thing that we can do, we can actually look into simpler models. So we're ignoring certain aspects and then determine a solution. This is of course a heuristic, but it's a very important heuristic because in mathematical modeling, our models can very quickly become extremely complicated. And if we can ignore certain features of the solution and still get a very similar solution, or even the same solution, this is actually beneficial. And what we're going to do is we're going to just leave out some aspects. And if we leave out the right aspects, then this is not too harmful to the solution quality. So for instance, what we can do is if we have the forests on the left and the workshops on the right and candidate sawmills on the left, we can actually solve two independent facility location problems. So for instance, we can first solve the facility location problem from the side of the workshop and then solve it from the side of the forest. But let's look into what kind of simpler models we could actually look into. The first model that we can look into is we're solving a facility location problem for assigning forests to the sawmills and a facility location problem for assigning the workshops to the sawmills. And what can happen then, if we're solving this for this example here on the right, is that we actually assign them to different ones, which first means that we actually somehow have to connect them. So we somehow have to correct the solution. But of course, also we have a little bit extensive costs. Another model that we can solve is we can first solve a facility location problem for assigning forests to the mills, and then a transportation problem for assigning the workshops to the sawmills. And now we don't have a second facility location problem, which makes it a little bit easier and ensures that we're actually feasible. So this is the first step, and then we're assigning, which of course means that in the second case we have slightly higher cost. And the last thing that we can do is we can just do the entire thing vice versa. So we can start with the workshops and use a facility location problem to place them. And then we can assign the forests to the sawmills. The problem with these slightly simpler models is, of course, that they might not be exact. So now let's look into how we're modeling this exactly. So what we're doing, if we model anything, we look into the recipe for formulations. We're identifying sets parameters. We're introducing decision variables. We're formulating constraints and the objective function. So which sets do we need in this so-called two-echelon facility location problem, where we're jointly considering the locations of the forests and the locations of the workshops when placing the sawmill? The first that we need is sets, which is of course forests, candidate locations for the sawmills, and workshops. If you're interested about these candidate locations, I'm just referring you to the previous video on facility location problems. The second thing that we need is parameters. And the parameters in this model, for that we can look back into the problem statement. So to expand their operations, they are operating one or more capacitated sawmills. So we're having a capacity. And they're connecting forests with a maximum logging. So we have some sort of supply capacity. and with customers which have a demand. So we also have a minimum amount that we have to ship to any sort of workshop. And then they're aiming at minimizing the total costs, which comprise of transport costs, opening costs, and handling costs. So what we know is we need capacities, we need supply, we need demand, and we need transport, opening, and handling costs. This then also just gives us the parameters, which we denote as OI, UI, and DI for supply, for capacity, and for demand. And then CIJ for the transport costs, and FI for costs of opening a sawmill, and GI for handling costs at the sawmill. And one slight difference to most other models that we've seen so far is actually this transport costs, CIJK. And here the important part is that we have this ordering. So we transport from forest to sawmill to the workshop, and this actually comprises the entire costs already. The next thing that we're doing is we're introducing decision variables. And in our case, the decision variable is XIJK, which is the amount of wood that we're transporting from a forest to a sawmill to a workshop. So the same thing that we also had with the costs. Secondly, we have this opening decision for a sawmill, which we denote by YI. Now we can start looking into constraints and objective functions, so into the actual math model. And the first constraint that we're seeing is demand satisfaction. So the amount that we ship towards the workshop has to meet the demand. Secondly, we do not want to exceed the supply, but we might actually leave some of the wood in the forest. So we are also saying the sum overall XIJK has to be less than or equal to the supply OI. And lastly, we have the capacity constraint, which, however, is linked to the opening decision. So obviously, if we don't open a location, we also cannot satisfy any sort of demand. And the last constraint that we always need is the domain restriction. So we're saying that the amount that we ship has to be non-negative, and the opening decision has to be binary. The last step that we're taking now is we're formulating the objective function. And the objective function in our case is total costs. So we're minimizing the total costs comprised of transport, opening, and handling costs. And this is what you're seeing here. So the first thing here is the transport cost, and then we have the opening costs here on the left, and then we have the handling costs here on the right. The opening costs only depend on whether a facility is open or not, while the handling costs actually depend on the amount that goes through the sawmill. What I would like you to take away is, first of all, how we can use simple models as heuristics. Secondly, I would like you to take away the two echelon formulation. And what we're going to do as an exercise is we're going to compare these different models. So we're comparing a facility location problem, a two echelon facility location problem with a network design problem. Thank you very much.